In this section, we are going to study partial fractions. By the end of this section, you should be able to split a proper fraction into partial fractions. A proper fraction is one whose numerator has a degree which is less than the degree of the denominator. You will need this skill in later topics in A-level maths, such as the binomial expansion, differentiation, and integration. In the previous section, called Algebraic fractions, we were combining two or more fractions into a single fraction. What you're about to study, partial fractions, is the opposite process. It is a skill whereby fractional expressions are split apart into separate partial fractions, each with a constant numerator. So for example, this fraction here becomes two separate fractions. They happen to be subtracted from each other in this particular example, but notice they have constant numerators. This is what we call a proper fraction or a proper algebraic fraction, because the degree of the numerator, which is the highest power of x in the numerator, in this case 1, is less than the degree of the denominator. And in this example, this denominator has a degree of 2. Although it is sometimes necessary to combine two or more fractions into a single fraction, like you learned to do in the previous section, we also often need to split a fraction into simpler parts, simpler separate parts like these, so that subsequent differentiation or integration can be carried out. And you'll be doing this later in the course, where you're given a complicated fraction like this. You need to first separate it into its partial fractions, and then that allows you to easily differentiate it or integrate it or possibly do other things. When we break up a fraction into two or more partial fractions, we use an identity sign, not an equal sign, as the expressions are equivalent for all values of x. Not just some values of x, but all values of x. So going back to the previous example where I used the word becomes, I'm now going to use the proper symbol, the identity symbol. So it means for all values of x, the left-hand side and right-hand side of this gives you the same values. We call it an identity. A couple of key points. First key point, if there is a linear factor of ax plus b in the denominator, this gives a partial fraction of the form something over ax plus b, that same factor. So going back to this example, our denominator, if you factorized it, which is an important first step, the denominator would become x take away 2 times x add 1. And going back to the key point, each linear factor gives us a single partial fraction. So the x minus 2 and the x plus 1 are our linear factors. Each gives us a separate fraction. So if you were doing this question from the start, just like we're about to do in the following examples, you would set it up by saying, we know it's going to look like something over x take 2 add something over x plus 1. And then you work out what the somethings are. Here I've called the somethings capital A and capital B. Second key point, it must be a proper fraction that we are working on. That's where the degree of the numerator is less than the degree of the denominator. Later in this section, we'll look at what you need to do if we have an improper fraction. But for now, just make sure you check, first of all, is it a proper fraction? First example, express this in partial fractions. First check, is it a proper fraction? In this case, yes. The degree of the numerator is 1, that's the highest power of x, and the degree of the denominator is 2. So yes, the degree of the numerator is less than the degree of the denominator. Here's the strategy I'm going to apply in each of the following examples. And I recommend you do the same when you start doing questions for yourself. First step, factorize the denominator if necessary. If it was already factorized, then obviously that step has been done for us. Here we have x squared plus 3x plus 2. That is not factorized, so we need to factorize it. So our first step is exactly that. Factorize the denominator. X plus 2 times x plus 1. First step done. Next, set up the partial fractions. Well, going back to the previous slide where we said each linear factor in the denominator gives you a separate partial fraction. Here I have two linear factors, x plus 2 and x plus 1. So I'm going to get two partial fractions with those denominators, x plus 2 and x plus 1. I don't know what the numerators are yet, so just think of a couple of letters and put them in the numerators. I could put plus or take away in between. It's simpler to put a plus. Next, combine the partial fractions. This uses the skill you were practicing in the previous section called algebraic fractions. So you were taking a couple of fractions that were added together or maybe subtracted and combining them into a single fraction. But looking at this, what common denominator would we use? Well, there's a little clue on the left hand side. X plus 2, x plus 1 is going to be our common denominator. So think about your right hand side and give each of those two terms the same denominator as we have on the left hand side. So the first fraction, we need to multiply the top and bottom by x plus 1. And for the second fraction, we need to multiply top and bottom by x plus 2. I'm going to immediately write them all over a single common denominator like this. So I've combined the two partial fractions into a single fraction. We get quite a long, complicated numerator, but that's just the way it is at the moment. Crucially, we should have the same denominator on each side, because that leads us to our next step. We can now make the conclusion that our numerators need to be the same. Remember, we're using the identity symbol here, which means the left hand side and the right hand side are identical for all values of x. Since our denominators are identical, then logic tells us that our numerators need to be identical as well. So the next line in working out is to say the numerator of the left must be the same as the numerator on the right. Now after practice, and once you get good at these and you're able to, then you could go straight from this line to that line. That will take practice though. And if you do try to start missing this line out, but that's causing mistakes, then abandon it and do it slowly step by step. Next step is to use substitution, or we could use comparing coefficients, which I'm not actually going to do in this example, but you'll see it in later examples, to find the constants. So we've got A, we've got B. Substitution is actually quicker than comparing coefficients in this situation, very slightly quicker. So what I'm going to do is choose a couple of values of x that will make one of these brackets 0. First up, I'm going to choose -1. So if I let x equal -1, on the left hand side I get 7 lots of -1 add 12, which is 5. But on the right hand side this term will be 0. And that's why I chose -1, because if this term will be 0, I'll have a multiplied by 0 which is 0. So a will not appear in the equation I'm about to write down. So sub -1 into the last bit, x is -1, add 2, you get +1, so b times +1. So we had 5 on the left equals 0 plus b, and there we go, we have b. So you might now think to yourself, what value of x could we sub in to make this bit disappear? That value is -2. Sub it into the left hand side, sub it into the right hand side. This term will be 0, and that means we'll be able to find a. So it gave us -2 on the left, it gave us -1a on the right, and from that we can work out that a must be 2. Now that's using substitution, and it is quite quick. Alternatively, we could compare coefficients. So if you were doing that method, then comparing the x terms on the left and right. On the left, the x term is 7. On the right, imagine expanding the brackets, we would have ax plus a plus bx plus 2b. So the x terms on the right would be a plus b. This is the comparing coefficients alternative method. We've compared the x terms, so you could compare the constant terms. On the left we have 12. On the right, the constant terms are a times 1, which is a, plus b times 2, which is 2b. Now you can see how this method takes longer because we now have simultaneous equations to solve, but it's an option if you want to use it. Now in later examples, sometimes I will use a little bit of comparing coefficients, but I haven't done in this example. So we found a, we found b. All that's left is to write down the answer to the question. Express this in partial fractions. Here is the answer. Second example, I recommend you pause the video and try and solve this question yourself. Think about the strategy we used in the previous example and apply it here. I'm going to work through the solution in 5 seconds time. Right, so here we go. A reminder of the strategy. Factorize the denominator if necessary. In this example, it is necessary. We need to factorize x squared minus 1. Well, that's an example of the difference of two squares. DOTS for short, difference of two squares. We have x squared, take away 1 squared, which factorizes to x plus 1 multiplied by x minus 1. So step 1 done, factorize the denominator. Step 2, set up the partial fractions. Each linear factor in the denominator gives you a partial fraction. We don't know what the numerators are going to be yet, so once again I have called them capital A and capital B. Just a quick note, it doesn't matter which way round you write these two fractions. I put the x plus 1 in my first denominator. It doesn't have to be the first, it could be the second, it really makes no difference. So if you did have a go at this question before watching my solution and you had a over x minus 1 plus b over x plus 1, don't worry, that's absolutely fine. So your final values for a and b should be the opposite to mine. So your a should be my b and vice versa. Combine the partial fractions is the next step. So the right hand side, give these fractions a common denominator, and the left hand side actually helps you with this. So that's what the denominator needs to be. So that's step 3 done, combine the partial fractions. Next, we can say the numerators have to be the same because the denominators are the same. and then use substitution or comparing coefficients to find the constants. Hopefully you had a go at using substitution because it is quicker in this case. So letting x equal 1 is a good idea because that gives you an equation where a doesn't appear. So from that we can find our value of b. And the other clever value of x is -1. Sub that in and we won't get b appearing in our equation. So now we know a and b. Make sure you finally answer the question. So it's 1 over x plus 1, take away 1 over x minus 1. You might have written that the other way around, which is absolutely fine. Minus 1 over x minus 1 plus 1 over x plus 1. That's the same as this, so it's absolutely fine. So well done if you did that before watching my solution. Now our third example, and once again I recommend you pause the video, try and solve this before watching my solution. I'm going to start my solution in 5 seconds. Strategy, step 1, factorize the denominator if necessary. Not necessary here, it is already factorized. To step 2, set up the partial fractions. We're going to get 2 of them here. It's not always 2, you could have 3 partial fractions, sometimes even more. So in this case, something over x and something over x plus 1. You might have written them the other way around. You might have written a over x plus 1 plus b over x, that's absolutely fine. Your a will be the same as my b, and your b will be the same as my a if you did it right. Now combine the partial fractions, give them the same denominator, which is going to be x plus 1. There we have it. Numerators need to be the same. And now we can start working out the constants. I recommend substitution because it is quicker. If we let x equal 0 here, then we're going to have b multiplied by 0, which of course is 0. So our equation will only have a. It won't have b. If we let x equal -1, then the a term will be 0, because it'll be a multiplied by 0, which will allow us to find b. We've got a, we've got b, so write down the answer. Now there are a couple more ways you could write this. Each of these 3 ways I'm about to show you, they're all the same, they all mean the same thing, so they are all correct. Now it's okay to put -3 in the numerator, but you'll find that mathematicians don't tend to write it like this. They tend to write it in the following way, a minus in front of the fraction. So minus and then 3 over x. It's just very slightly neater. So this would be perfectly correct. I think an even neater way is to put the positive term first. So the positive term is the 10 over x plus 1. I'm going to write that one first. And then the negative term. So once again, each of these 3 versions, they're all the same, they're all correct. I just think that last one is the neatest.